In this video, I'm going to give a brief introduction to the metric system, especially for those people in the United States, right? Where for us, the metric system is far less intuitive than maybe we would like it to be. Especially for people learning physics for the first time, one of the most common complaints I hear is, well, if I'm measuring the speed of something, why do I have to use meters per second, right? Because feet per second or miles per hour, these things at least make sense to people in America, right? So why are we saying things in meters per second? You know, it just makes it very hard to understand and get a grasp of what's going on. And the truth is, yeah, it is difficult, and you could just do feet per second or miles per hour, but also in truth, it very much complicates the calculations that you make. The metric system is ideal for physics, and that's the truth. And so part of that is because we have base units and derived units that make everything so simple for us. And so let's talk about the base units first. So base units are kind of the fundamental units of the metric system. So the first one is the meter, and that's for measuring length. 2, seconds, no surprise, for measuring time. 3, we have kilograms. Okay, and I'm gonna make a point here. It is interesting that the base unit for length is meters, and then this one is kilograms. And what do I say that? Well, a kilogram is 1,000 grams, right? That prefix, kilo, is 10 to the third, or 1,000, right? Same thing. But for meters, why not do kilometer, right? Why are we gonna do kilograms but not kilometers, right? And there's good reason. It's because the derived units that we have make use of meters more than they do kilometers. In fact, they never use kilometers, and also the derived units use kilograms. And so these things are more fundamental to everyday life, and so that's why we use meters and kilograms instead of kilometers and kilograms, also instead of meters and grams, right? And so if that doesn't make a ton of sense to you right now, just bear with me for a while. And again, at the very start, it doesn't always make sense, right? It's not always 100% certain why we're doing that, but there is great reason for it. And it does simplify your life immensely by using these base units. And so the fourth unit is Kelvin, and that's for measuring temperature. And I just want to briefly note that Kelvin is not degrees Kelvin. There is no such thing as a degree Kelvin, very much unlike degrees Celsius and degrees Fahrenheit, right? Kelvin is measured from an absolute zero, and Celsius and Fahrenheit are not. They are degrees relative to boiling points and freezing points, but Kelvin is measured from an absolute zero temperature, and so it is not degrees, it's just kelvins. Now, the fifth one is very much uncommon for us. It's a mole. It's the amount of like a substance. And so for a mole is 6.022 times 10 to the power of 23 molecules, right? Or atoms or whatever. So 6.022 times 10 to the power of 23. It is a big number, okay? And then number 6 is the candela. Now, candela is used to measure luminous intensity or luminosity. And so we really don't need that for our purposes right now, but in different physics later on, it becomes more important. And then finally, the ampere is for electric current. Okay, that one's less useful for us right now, but it very quickly becomes useful. But I'll leave it at that. So those are our base units. And then we said, well, there's also derived units. So derived units are units that are made by combining 2 or more base units. Okay, so one example would be the Newton. Okay, so Newton. Newton, yes, obviously the name of the physicist, Isaac Newton, but there's a unit named after him, which is just the Newton, or an uppercase N. And what is it? Well, a Newton, and I'm putting these brackets around to let you know that I'm talking about units here and not an actual quantity, not an actual number. So a Newton is a kilogram times a meter divided by a second divided by another second. So kilogram meters per second squared is how we would say that. Kilogram meters per second squared. And so that is how you define a Newton. So as I mentioned earlier, all we did is we took kilograms, we took meters, and we divided that by seconds squared, and you do that and you get a Newton. Okay. And so what else is there? I'll give a couple more examples. The next one would be joules. All right, and so what is a joule? It's actually very similar to a Newton. The only difference is that it's a kilogram times meters squared per second squared. All right, so that's a joule. And this one should be more familiar. What about watts? Well, a watt is equal to a joule per second. Okay, and so that is, if I wanted to write that out even longer, kilogram meters squared per second squared divided by seconds. Okay, or per second cubed, you could write. Okay, so those are examples of derived units. There are so many derived units, and this is what I was talking about earlier for why we don't use grams, why we use kilograms, right? This is how we've already defined newtons and joules, is with kilograms in them. And so these base units are in kilograms, not grams. Okay, and so it does simplify, as I said, the calculations to be more reasonable for the things that happen in everyday life. Now, when you get into more advanced physics topics, sometimes we have to make even weirder derived units. So for example, the angstrom, and I'll just make a quick note of this, is equal to 10 raised to the power of negative 10 meters. Okay, and so that is an angstrom. And that's useful for things like particle physics or materials physics, which are very, very small scale. Okay. A ton of grams. We got a lot of grams. And so how are we going to do that? Well, what's the most effective way? Well, we're going to have to add a prefix. And so if we go up, let's say 1,000 grams, we're going to do kilograms. If we need even more than that, we'll say this is equal to 10 to the power of 3, or 1,000. If we need more than that, we're going to use the prefix mega, which is 10 to the 6th. If we need more than that, we're going to use giga, which is 10 to the 9. And you can actually go further than that. I'm going to stop there because these are easily found online, and this is all we need right now. But let's say smaller than grams. Well, we can use milligrams. Okay, and that's 10 to the negative 3, so 1/1000th of a gram. Let's go smaller than that. We need micrograms. Okay, that's 10 to the negative 6th. Smaller than that would be nano, and that's 10 to the negative 9. Okay, and as a quick note here, let's just say that we were talking about meters instead. Well, very often we go centimeters, and that's actually 10 to the negative 2. That's one of the only ones that doesn't go in a power of 3. So 369, 369, these powers of 3 are super common. This one right here is strange because, as I said, a centimeter is a 10 to the negative 2. 10 to the negative 2 meters. And so it's a more strange prefix, but it can get the job done depending on what we need. And so the point is here, when you're doing calculations in physics, it's generally really good when you're starting off to bring everything back to these base units. Put everything in kilograms, meters, kelvins, moles, candelas, amperes, seconds, whatever, right? Don't use hours. Don't use kilometers, for example. Don't use any of those. Use your base units, right? These are important. This is how you want to make calculations. And so if you are given a problem that tells you something in kilometers, right? And let's say it gives you a distance, for example, 4.2 kilometers, and you are asked to make some calculation using that distance. Well, you don't want to plug in 4.2 anywhere in your solving, in your problem solving. You want to do something like 4.2 times 10 to the 3, or just more simply, 4,200, right? And how did I do that? Well, you just take 4.2, move the decimal over 3 places, right? So 1, 2, 3 places, 4,200.0 meters. Okay, so make sure that those units are put into base units before you make any calculations. Otherwise, you will get it wrong. You will get a wrong answer if you're not careful enough with your units. Okay, very easy mistake to run into, mistake to make. So let's talk more about the why for a second. I just want to bring up 3 points. Number 1 is consistency. Scientists throughout the world use the metric system. If we are consistent in using it with them, then we can compare results with them, and that is super important. Number 2 is accuracy. So accuracy is also important because these kilograms, it's not just like somebody gave a best guess for what a kilogram is. These things are really well defined. A meter is super well defined, and that's a really interesting to read about. A meter is actually defined by the speed of light. And there's more to it than that, and I don't want to get into that explanation, but the speed of light is a constant. And so if you take how many meters light travels in a second and you divide that into a certain number of segments, you can essentially get to the definition of a meter. And that is a really well defined and standardized unit. And then the final thing is simplicity. And it's very easy to switch between units in the metric system. For example, from kilometers to meters. Very, very easy. And so simplicity is a great friend of the metric system. And so definitely, especially when that question comes up of why not use feet per second? Well, it's to make your life easy, right? And so this is just a really brief introduction of the metric system, and hopefully you enjoy it, and I'll see you next time.